Hey y'all. Okay, so we are going to, I didn't know that was my background. We are going to do 5.1, which is systems of linear equations in two variables. So let's just go ahead and kind of define a few things. All equations ax plus by equals c are straight lines. A system can have exactly one solution. This means that they intersect at one point. These systems are consistent, independent systems. The systems can have no solution. This means that they are parallel lines, and this system is an inconsistent system. Let me just go and write this. Hold on. Hide. So, and then we also have systems that have infinitely many systems. I'm sorry, why did I say that? Infinitely many solutions. Usually INF many or IM infinitely many. Infinitely is a pretty large word. No one wants to write it over and over again. If you have a system that has infinitely many solutions, this means they are identical lines and they are consistent, dependent systems. Okay, so for that first example, hold on, let me just get this real quick. Okay, for that first example, when it has exactly one solution and it says it intersects at one point, what you have is you have a line and then here's another line, right? They intersect at one point. And then for a no solution, what you have is parallel lines. And then for a system that has infinitely many solutions, what you have is one line and another line right on top of each other, right? They're identical. They're the same lines. And that's whenever you have infinitely many solutions and it's considered consistent, dependent. Parallel is inconsistent. And then consistent, independent means that they cross at one point. Okay. So the first thing that we're going to do is we're actually going to check to see if the point 4 comma negative 1 is a solution for this system. I don't want to zoom out too much, but that's where we're going. Okay, so what we're going to do to check to see if 4 comma negative 1 is a solution is actually just plug in 4 and see if it works, right? And then we're going to plug in negative 1 and see if it works. So we know that for this coordinated point, that is our x and that is our y, right? So let's go ahead and plug in x and plug in y. Okay. Okay, sorry. If I'm trying to figure out where I want to really write this, I think I'm just going to kind of write it to the right, okay? If we plug in 4 for our x, we would do 4, and that's plus 2 times y. We're saying y is negative 1. We're going to see what that equals, okay? And then right here, let's go ahead and plug in 4 for our x, negative 2 times y, which is negative 1. We're going to see what this equals. So on that top equation, we would have 4 plus 2 times negative 1. It's going to give you a negative 2. Here, I'll just do each step. We have 4, 2 times 1 is 2. Signs are different, so it's negative. And what we would end up getting is 2. And I also have a 2 right here, so that checks out, right? Then on this bottom equation, we have 4 minus 2 times negative 1. So we have 4. Okay, so we have 2 times 1 is 2. Signs are the same, so it's positive. And whenever you add those together, you get 6. And I notice right here that I get 6. So the answer would be yes, 4 comma negative 1 is a solution. Okay, so now let's look at the substitution method. for the substitution method, what we do is we're going to solve an equation for a variable. And then what we're going to do is plug into the other. So whenever we like solve for y or solve for x, we plug in for y or x. There's really no way to say for sure you always solve for x or you always solve for y. You're really going to look at your equations and you're going to see which one's the easiest one to solve for. And then whatever variable you solved for, you plug in for that variable into the other equation. And then after you solve that equation, what you're going to do is plug the answer that you get into the two original equations. You just pick one. So you plug into the original. So it'll make more sense when we do a problem. But whenever we solve for one variable, say y, and then we get an answer, that tells me y equals something, right? Plug in that answer into one of the original equations. And what that'll do is end up giving you your x. And then vice versa, if you solve for x first, whenever you plug in a second time, what you'll actually be getting is your y variable. Okay, so let's go ahead and do that. What I notice, there's a few different ways you can go about this. In the homework, I think they kind of number these each time. I'll do that. Y'all let me know if it ends up being too confusion. I am confusion. If it ends up being too confusing, okay? So let's go ahead and label this equation 1. Let's call this equation 2. What I'm going to do is I'm going to take equation 2. The reason why I'm going to take equation 2 is I noticed that in equation 1, both variables have a coefficient. So that lets me know that equation 2 is probably going to be a little bit easier to solve for. And what I would be solving for is the x, because it's just 1x, right? So I'm going to take equation 2, and I'm going to solve for x. Okay, so let's go ahead and write down equation 2, which is x minus 2y equals a negative 3. In order to solve for x, I need to actually isolate that variable. And so what I'm going to do is I'm going to move that negative 2y to the right-hand side. And so now what I get is x equals 2y and a minus 3. Okay, so what we're going to do is actually call this equation. Let me do this, y'all, just so maybe the different colors can help a little bit. Let's call this equation 1, this equation 2. We're going to take equation 2 and we're going to solve for x. Okay, I have solved for x. Let's call this equation 3. And so now what I'm going to do, the directions told me to solve an equation for a variable. I just did that. And it says plug into the other. So what I just now solved for x, I'm going to plug into the other equation. I used 2 to solve for x. So now I'm going to plug my answer into 1. Okay, so I'm actually going to go, let's go right here. Okay, we're going to plug 3 into 1. Okay, we'll do all the math in purple. So plugging 3 into 1, let's look at my equation 1. I have 5x minus 4y equals 9. Well, for equation 3, I have it solved for x. So what I have is 5, open your parentheses. Your answer is going to go into that, okay? It's going to be 2y minus 3, close. Look back up at equation 1. What I have left is a minus 4 equals 9. And then, y'all, this is going to be distribution, right? What I'm going to do is actually distribute this 5 into both of those terms of that binomial. So I would do 5 times 2 is 10. Signs are the same, so it's positive. No y times y is y. And then 5 times 3 is 15. Signs are different, so it's negative. And then what I have remaining right here is going to be brought down. So my goal is now, if you notice, the only variable I have here is y. So in equation 1, I had 2 variables, right? Whenever I came up with and solved for equation 3, I solved it for x. When I plug that into 1, what happens is now all I have is y's. I can just solve this like a normal equation, right? So I notice it on the left-hand side. What is that? Okay. I notice it on the left-hand side. I have 10y, I have a minus 15, and I have a minus 4y, right? Like a negative 4y. So I'm going to go ahead and combine my like terms. 10y minus 4y gives me 6y. I'm going to move that 15 over. That makes it a positive 15, which gives me a positive 24 on the right-hand side. I'm going to divide both sides by 6, and what I get is 4. So this right here is my y. Okay. Now I know that whenever we solved equation 2 for x, if you look, we actually got an expression on the right-hand side. We didn't just get an actual, let me move up, y'all. We didn't just get a value. We got an expression. But what we want to do is take this y and plug it into an original equation. The one I'm going to plug it into is the second one because, again, simpler equation. And what we end up getting, so let me go ahead and write this, though. We're going to 1, 2, 3. Let's call this equation 4. I know it's just y equals a number, but that equal sign means it's an equation, okay? So we're going to plug 4 into 2, okay? Now the solve for with this equation, the plug into this equation, those will be different and completely unique for every single system of equations. I'm just kind of showing you the steps that I'm doing. You always want to pick the easiest one to solve for, and then once you do solve for a single variable, you will plug it back into original, but it just might not be the first one. It could be the second one. It's always going to be different, okay? I'm just going to always pick the simplest one because it's simplest. So now let's actually plug equation 4 into 2. So what I get is x, right? And then minus 2, open, what's my y? My y came from equation 4, which is 4, close, equals negative 3. Now, I only have one variable. Equation 2 started with 2 variables, but plugging in for my y, now I only have one variable. And it's a good thing that the only variable I have left is x, because I need an x and a y to actually to write my answer, right? I already have my y right here. Now I'm trying to solve for my x. So we would get x, and we have 2 times 4 equals 8. Signs are different, so it's negative, equals negative 3. Moving my negative 8 over, it would become positive. Those signs would be different, so you would subtract, and you would keep the sign of the larger number. That is my x. Now, the way that we're actually going to write our answer is going to be, I don't know what color we want our answer to be. Red just seems so like, rawr, but it's probably going to be the one I pick. Okay, so our answer for this system of solutions, what? The solution to the system of equations is going to be written in a coordinated form, right? It's going to be our point. Our x is 5. Our y is 4. Close it, and then you do your other brace. And so that would be the answer using the substitution method to solve that system of equations. Okay, so now what we're going to do is called the addition method. So for the addition method, we're going to combine the equations to solve for a variable. In my little parentheses there, it says multiply by coefficient if needed. Plug solved variable into an original equation to solve for the other variable. Okay, so I notice here that if I'm going to combine these equations to solve for a variable, this is a fairly simple example. We're doing all of our work in purple, right? Combining adding, subtracting, right? They're already written on top of each other, which means that the like terms are already listed per column. So the only thing I really need to do, is just go ahead and I can draw a line underneath them and I can combine them. You don't want to just simply combine. This one I know I can, and I'll tell you why. Other ones you may have to, like it said, multiply by a coefficient. Y'all, if you actually go through here and combine like terms, do you notice those first terms, 3x and a negative 3x, those are additive inverses, right? They're the exact same term, but they have a different sign. So they're going to cancel. They're going to go away. Now we're just looking at our y terms. I have a negative 4y, and I'm going to combine it with a positive 2y. Signs are different, so I would subtract, keep the sign of the larger, keep your variable, keep your exponent. Our equal sign comes down, right? We're also going to combine our c's, our constants. So if you combine 11 and a negative 7, signs are different. So you subtract, you keep the sign of the larger. I haven't actually solved for a variable yet because what I have is a negative 2y. I just want y. So wouldn't you just divide both sides by negative 2? You get 4 equals, if you divide 4 by negative 2, 4 divided by 2 is 2. Signs are different, so it's negative. So this is my y. It told me to plug the solved variable into an original equation to solve for the other variable. Both of those equations are pretty much similar. One doesn't have like a 12 or a 15 as a coefficient. Like the math is going to be pretty much the same regardless of which one you decide to plug into. I would rather that to be purple. And so let's go ahead and, that leading coefficient of that first equation is positive. So let's just pick that one, okay? So what we would have is 3 and then x and then our minus sign or our negative sign, 4, open. This is where we plug in our negative 2, close, equals 11. Okay, so now let's actually solve this equation for the variable x because all we have left in this equation is x. So I have 3x, 4 times 2 is 8. Signs are the same, so it's positive. Our equal sign and 11. Move our 8, it's positive, which means it'll be negative. We would get 3x equals, for 11 being positive and a negative 8, signs are different. You subtract, keep the sign of the larger, and then we would divide both sides by 3. We get x equals 1. The reason why the first step that we did was check to see if something was a solution was because right here, if you just kind of aren't completely sure what you're doing, you could actually plug in this point, 1 comma negative 2, to these equations, into both of them, and see that it does check out and see that it is a solution. That right there would confirm that your work is correct. Okay, so as far as like giving the solution set as an answer, what you would do with our very loud red is my x is 1, comma, my y is negative 2, close, ugly brace. A little bit better. And so I didn't know if I squared that one off or not. So that would be your answer. Okay, so let's go ahead and do a second example using our addition method. This example is very important. The one we just now did, we had additive inverses, which means it was fairly simple. Draw a line underneath them, combine them, plug your answer back into the original, like one of the originals, right? So when I notice here, like if I combine these, y'all, for my x term, I'm going to get what? I'm going to get 12y. And then I'm like, okay, well, maybe I'm not supposed to, do that one. I'm supposed to be more concerned with the y. So what do I get over there? Well, signs are different. I would subtract, and I would end up getting a negative 6y. So I'm not solving for a variable per se. You could still do it because here is, sorry, I was trying to blow that off, an example of having like negative 2y, and then I went ahead and just solved it some more. But what you can do also, the reason why we divided both sides by 2, I still only had one variable here, right? My goal is to cancel one of these variables, and then whatever you need to do within the equation, that's fine. But that shouldn't be your train of thought with this. You should be able to have an additive inverse and cancel one of these variables. Well, I do know that 9 is a factor of 3, which means that I could multiply 3 by something, and then I would be able to cancel that 9. Well, if I multiply 3 by 3, I get 9, right? But if I combine 9 and 9, I get 18. So I actually need to multiply this first equation by a negative 3, right? Let's go ahead and do that, and you'll see why this works. If you go ahead and distribute that negative 3 through, I'll go ahead, of course I skip steps because I always do. I'll go ahead and I'll rewrite that first equation and then the second one, and then that's where we will actually go ahead and combine them, okay? So let me move this way. If you distribute that negative 3 in, you get 3 times 3 is 9. Signs are different, so it's negative. No x times x is still just x. 3 times 2 is 6. Signs are different, so it's negative. No y times y is y. And then right here, if you do 48 times 3, you get 144. Signs are different, so it's negative. You're done with that equation. You're literally just going to write the second equation, not multiplying anything to this equation. I pretty much just manipulated that first equation so that I would have additive inverses and so that I could get rid of one of the variables. So now what we can do is just go ahead and combine. What you get is if you combine a negative 9 with a positive 9, is that they cancel. And if you combine a negative 6y and a negative 8y, those signs are the same. So you would just add them, keep their sign, keep your variable, keep your exponent. And then on the right-hand side of the equal sign with my constants, I have 144 and I have 24. They're both negative, which means signs are the same. What you do is you add them together and you keep their sign. I'm solving for y. So what I'm going to do is divide both sides by 14, but not just a positive 14, a negative 14, right? And if you do that, what you get is y equals 12. That is the value for my y. Don't think I have, I didn't think so. I'm actually, y'all, going to move now over here to solve for my x, okay? So to solve for my x, what I do is I take the solved variable that I just found and I plug it into one of the originals, okay? That means those light blues. I would not plug it in to that equation. I would plug it into one of the original equations. I'm going to pick the first equation because it has smaller numbers that are attached to the variables, right? That's going to be where my multiplication comes into play. So let's actually do that. Am I purple? I'm purple. There's something on my screen. Okay, first equation says 3 times x, and then a positive 2y. Well, we have 2 times our 12 equals our 48. Pretty much just rewrote equation 2, plugging in the y, right? So if we actually solve this, I have 3x plus, I was going to do the 4 first, I messed up. Plus 2 times 12 is 24. Signs are the same, so it's positive. Equals 48. I would actually move that 24 to the right-hand side. So I get 3x equals 24. And then here I would divide by 3, and I get x equals 8. And so x equals 8 is the answer here, which means our final answer is 8, 12, close brace. That makes sense, y'all? Okay, so, sorry, it's like really late right now. I want to scroll back up to the top, y'all. I want to show you again those definitions. We checked to see if something was a solution to some equations. Right here, we actually used a substitution method to find a solution. We also used the addition method to find the solution. Now what we're going to do is kind of use our definitions more. If I can scroll up. Okay, right here. I guess kind of like the dark blue. The different types of solutions that we have are a consistent independent system where they intersect at one point, which means they have exactly one solution. Okay. And then we have an inconsistent system, which means the lines are parallel and there is not a solution, right? So this is my one solution. Okay. And then the fact that these don't cross anywhere means that there's no solution. And then the fact that these constantly touch at all points means that it has multiple solutions, infinitely many, right? Because there's so many points that they're touching at. So they don't touch anywhere. There's no point. They touch one place. There's one point, right? One solution. They touch everywhere. There's infinitely many. Okay. So with the infinitely many solutions, which means that we have identical lines, that would actually be called a consistent dependent. They're dependent on each other. They're consistently dependent on each other, right? This is a consistent line. Both of those do the same thing consistently at the same time. They're dependent on each other. This one would be inconsistent because there's not a point, there's not a solution. And then our exactly one solution that has the one point, that's consistent, but they're independent, right? They don't depend on each other. They're not on top of each other. They do still have a solution, which is why we say consistent, but they don't depend on each other, okay? Okay, so we're going to actually solve a system of equations, and we're going to be able to state the type of system that it is. So it's a solve solution. Oh, sorry, I was moving my legs. Solve system and state type. So when I look at this and I think, okay, so if I wanted to do the substitution method, I could solve for a variable, plug in, plug in. I could also do the addition method, which automatically cancels one of my variables. And I think what I want to do is multiply. I'm trying to think. So if I do 4 times 3, right, I'm looking at the first equation. If I do 4 times 3, I get 12. And if I do the second equation by 2, I get 12. But it wasn't just using one coefficient and, oh, hey, now look, I've got an additive inverse, right? Here, I'm actually going to need to multiply both of these equations in order to have the ability to like cancel a variable. So if I multiplied the first equation by 3 and the second one by 2, I'd actually have two positive 12s, right? I need one of them to be negative. So what we're going to do, this one I'm going to kind of do a little bit more labeling than we did before. We're going to call this equation 1. We'll call this equation 2. I'm actually going to multiply 3 times equation 1, and I'm going to multiply a negative 2 times equation 2. So let's go ahead and do that math and then just kind of, see what we're looking at there. So if you multiply 3 times equation 1, right, same way we did in that previous problem, every single thing gets multiplied by 3. So that'd be 4 times 3 is 12. X times no x is x. 6 times 3 is 18. Sides are the same, so it's positive. Y times no y is still y. And then we have 12 times 3, which would be 36. Signs are the same, so it's positive. And then now let's go ahead and do a negative 2 times equation 2. Okay, so 6 times 2 is 12. Signs are different, so it's negative. So that's great. Kind of looking like an additive inverse there. And then I have no x times x. Well, that's x. And then I have 9 times 2 is 18. Signs are different, so it's negative. And then I have y times no y, which is y, equals, okay, so now we have 12 times 2 is 24. Signs are different, so it's negative. Okay, so now that looks a little bit better. I've got an additive inverse. I can literally go ahead and combine these, right? And then I'll do all the other steps that it says to do, whatever's required. So let's go ahead and combine these. If you combine a positive 12x and a negative 12x, what happens? Same exact term, different signs. Oh man, trying to change channel. So what happens is that they cancel, right? It's like you got $12 in the bank and you bought lunch, you got none dollars, right? Okay. So that went away. Now let's look at our 18y and our 18y. One's positive, one's negative. It's the same exact thing just happened there, right? Those are also additive inverses. So I literally just took away both terms on the left-hand side. So what I need to do is I need to indicate that with a 0 because both of these completely canceled each other out. Both sets of those numbers, right? Both pairs. So if you look on the right-hand side, I have 36 minus 24. Signs are different. So what you would do is subtract, and you would get 12. Keep the sign of the larger, which would be positive. So if you notice here, this is saying, like, don't draw a slash through your equal. If you do that, it makes it true, right? But I don't want to know that. What I want to know is exactly what does this say? This says 0 equals 12. Does 0 equal 12? Like literally anywhere? No. So we could say that this is a false statement, right? That's false. 0 does not equal 12. 0 equals 0. Okay, so this would be saying what? This would be saying that there's no solution. That was supposed to be an L. This is saying that there's no solution. Well, I know for a fact that if there's no solution, this means that my system is inconsistent. It takes me a while to scroll up, y'all, so look right there on your notes. This means that the system is inconsistent. And there's something else that you might see in the homework. And please, y'all, let me write it first, and I'm going to highlight it, okay? This is how do you say it? Another way of stating that it's a false statement, that it has no solution, and that the system is inconsistent is to say that the solution set is an empty set. This symbol does not mean 0, and it does not mean undefined. It literally means that it's empty, okay? So that is very important. I've seen a lot of zeros being turned into this, and that makes it completely wrong, okay? So the reason why it's false, there's no solution, it's inconsistent, and the solution set, right? These are solution sets, y'all. That's a solution set, right? I was able to find a solution. I can't find a solution here, so it's empty. The reason why is because 0 does not equal 12, okay? Okay, so let's do this one. Same thing. We're going to solve this system of equations, and then we're going to state the type that it is. Okay, so do you kind of notice something with this problem or, this system? Usually what I would do is, like, let's use addition method, cancel a variable. Let's start doing what we need to do to solve for a variable with substitution and then plug it in. Okay, so that's already solved for a variable, right? So they've already kind of done a good chunk of my work. What I want to do, just to make things clear, is let's call this equation 1. Let's call this equation 2. Because equation 1 is already solved for a variable, what I can do is actually just plug equation 1 into equation 2. So looking at equation 2, I have 15x minus 5y equals 10. So let's plug that in. My 15x is 15x minus 5 times y, but I'm plugging in y. Then we have equals 10. So using distribution, right? What I'm going to do is I have my 15x. 5 times 3 is 15. Signs are different, so it's negative. No x times x is x. And then 5 times 2 is 10. Signs are the same, so it's positive, equal 10. Okay, so on the left-hand side, okay, so if I combine like terms, do y'all see how these are already additive inverses, right? 15x minus 15x, same exact term, different signs. They just canceled each other, right? They just went to 0. So what do I have left on the left-hand side? I just have a 10 equals on the right-hand side. On the right-hand side, I have a 10. Question, does 10 equal 10? Yes, it does, right? It's the exact same value. So we could say that this is a true statement because it is. 10 is 10. Okay, so this right here, the solution set could kind of look a little messy. I'm going to write it both ways, and I'm going to try my best to really explain it. Let me just explain the answer, and then I can go back and add just a little bit to those definitions, and it'll make more sense, okay? So this is a true statement, right? This is actually going to have infinitely many solutions. And the solution set, I've got 2 different ways that I could write it. We're going to actually do it in set builder notation. This is saying that for all x and y, such that y equals 3x minus 2, right? That's one of the solution sets. And I get that from right here. Okay. Or what we could say is for all x and y such that, let's go ahead and write our second equation, which is 15x minus 5y equals 10. If you notice here, y'all, this is just equation 1, right? And this is just equation 2. So if you have infinitely many solutions, your solution set can say that your point can come from equation 1 or your point can come from equation 2. And because 10 is 10, it is a true statement. So now let me kind of scroll back up there and let me show you something. And I believe it'll really clear that up right there. It's just kind of something else that I think should be added to the definition. All the way up here. We're going to scoot like that. Excuse me. Okay, so exactly one solution, right? This is an example. This doesn't mean it will always be written like this, but an example of exactly one solution would be similar to x equals, we're just going to say a number. I'm actually going to do that pound sign. It's a little bit better, right? We got y equals a number. No solution is going to be a contradiction. Okay, that was like when we got 0 equals 12, that was a contradiction, right? That's not true. It was false, no solution, inconsistent. Okay, if we get x equals 4, well, that also means that we have the ability to find our y, right? So when we see that x can equal a number, we have the ability to solve for the other variable, and that would be considered having one solution and that it would intersect at that point. Okay, infinitely many solutions. I'm trying to think the best way. I tell my elementary algebra students, it's going to be like 0 equals 0, 2 equals 2, 4 equals 4, 5 equals 5. That's literally just saying that you have an infinite amount of solutions. If I could think of an easier way to say that, I will make sure I add a note on this video or send an email. You know I love sending emails. Something like that, okay? So whenever I get to the problem I was working on, 0 equal 12, no, inconsistent, right? Then right here, 10 equals 10. That's in the form of like the same number equals the same number, 0 equals 0. So that would mean that there's infinitely many solutions. I have no idea how long this video is. I think I'm going to just finish it. Okay, so let's do this word problem, then we're done with 5.1. So a 6,000 seat theater sells tickets for $28 and $40. How many of each for a sold out event with a profit of $188,400? So it's gonna be a couple of different things we need to like declare, right? And like state what they are. And then it'll be very similar to the problems that we just did. Well, I have two different prices for tickets, right? And I'm dealing with section 5.1, which is a system of equations with two variables, right? X and Y. So what I'm going to do is I'm actually going to say that the tickets at $28 is X, right? And what X is representing is the total amount sold, right? The total sold at that price. And so similarly, what I would say is that the tickets at $40 would be what? Yep. And Y is going to be the total sold at that price. Another thing that we're going to do is we're going to let total revenue be T. Okay, it's the total. Now let's go ahead and let's put this into, stop. Sorry. Let's go ahead and let's put this into a certain form. So what we have here is T equals, right? That's the total revenue equals 28X plus 40Y. And I know this, excuse me, I know this because I sold both tickets at both prices. I'm trying to figure out what the total amount of X and the total amount of Y is. And I know that whenever I do solve it, their price needs to be at a combined 188,400, right? 188,400. Okay, so very important now, what we have is we need to know that the total amount of revenue, we'll just keep doing it in purple. The total amount of revenue is 188,400 equals however many $28 tickets we sold plus however many $40 tickets we sold, right? Now, how could I even tell what the possibility is of like the combination of $28 tickets and $40 tickets, right? It's not just some random number. It told me that there's 6,000 seats. So however many tickets I sold at $28 plus however many tickets I sold at $40, those total amount of tickets need to total to 6,000. And then the actual price, once I multiply those totals to the amount they were sold for, needs to total that total revenue, right? Okay, so what we're going to do is we're going to actually call this equation 1, and we're going to call this equation 2. So the first thing that we're going to do is I'm going to notice that I do not want to do the addition method here. In order, y'all, to cancel, say, the x variable, I would need to multiply equation 2 by negative 28. That's not pretty. In order to cancel or solve for the other variable, I would need to actually multiply equation 2 by negative 40. Do you see how that doesn't seem very feasible, right? But I do know that with the substitution method, if I can solve for a variable, all I've got to do is plug it into one of the original equations, and then with that answer, plug it into an original equation again, and then I'll get whatever my x value is and whatever my y value is. So looking at this, I'm just going to go ahead and I'm going to solve. I'm going to scoot up, y'all. Okay, we already have our equations written. I'm going to solve for x, and it's hopefully obvious that we would use the second equation to solve for x, not the first one, right? So let's do this. Did I write all of it in purple a minute ago? Whenever I said solve for and stuff like that? No, I did it in blue. Okay, so let's solve equation 2 for x. Okay, so equation 2 solved for x means I'm just going to move that y over, right? So I'm actually going to write both of them. Equation 1 has not changed. It's still the exact same. Equation 2, I'm solving for x, which means I would have 6,000 minus y equals x, right? Now that I have this solved for a variable, we have been declaring it a new equation. Let's call it 3. What I'm going to do now is plug equation 3 into equation 1. If you do ever look at an example like for help, they may refer to this as back substitution, Okay, so let's go ahead and plug equation 3 into equation 1, right? Where's my equation 1? Right there. We'll just go ahead and continuity. That's 1, right? Okay, so let's plug equation 3 into equation 1. Equation 3 is solved for x, so we're going to write equation 1 until I see an x. I get 188400 equals 28 times x. I already solved for my x. It's 6,000 minus y, close, right? That would be it. That's my x. And then I notice that I have a plus 40y. Okay, so now that I've gotten here and I notice that all I have is one variable, I can just solve it like a normal equation, y'all. Okay, I know that that number is touching a parenthesis, which means to multiply. Left-hand side, 188400 equals. Right-hand side, if you do 28 times 6,000, what you get is 168,000. You do 28 times a negative y, what you get is a negative 28y plus a 40y. I notice on the right-hand side I have common terms, so I'm actually going to just write my left-hand side the way it is. My 168.23. Okay, so negative 28 combined with a positive 40, signs are different, so you would subtract, keep the sign of the larger, keep your variable, keep your exponent. And then what I would do, I started to just use my calculator here, y'all. I subtracted my 168,000 from both sides. And then what I did was I divided both sides by negative 12. Okay. I just had my calculator. I typed 188,400 minus 168,000, enter. Now do divided by negative 12. What you will get, 1,700 equals y. That is the number of tickets sold for $40. Now what we're going to do is we're going to take what we just now solved for our y, and we're going to plug it into an equation. I would use equation 2 because it's simpler. Okay, so you know what? Let's go ahead and do this just so I can kind of be close to equation 2 right here. I got 1700 for y. So what I get is 6,000 equals x plus 1700. Solving for this equation, wouldn't I just subtract 1700 from both sides? So what I get is 4,300 equals x. So that is my, what was that? That is my x, which means that the solution set would be, pay attention there, I almost said 1700, but that was my y. Okay, my solution set is 4,300, comma 1700, where 1700 is my y, and then 4,300 is my x. So what I want to do is just kind of a couple of little checks, right, just to make sure. This is saying that 6,000 equals 4,300. Sorry, let's do it this way. Yes, that was right. I'm sorry. 4,300 is my x, and then plus my y. And if you add those together, I get 6,000, which is true. And then time-wise, I'm not going to actually do this, but if we plugged it in here, I would get 1884 double 0 equals 28 times 4,300, close, plus 40 times 1,700. Go ahead and check that in your calculator. You should get 1884.00, which means that the number of $40 tickets that they sold was 1,700, and the number that they sold of $28 tickets was 4,300. I wouldn't try to just sit there and start multiplying 28 by something and 40 by something. I've seen people do that. So let's do 28 times 10, 28 times 20, 28 times 40, 28 times 50. Oh, that would mean the $40 tickets had to be 80 or 90. You're going to go down a rabbit hole, and it's going to take you quite some time to get to 4,300 and 1,700, or either or. So don't do that, okay? That is it for 5.1. If y'all have any questions, make sure y'all email me. Okay? Thanks. Bye.